Hello friends. Now today we are discussing about the strain energy. Now as we know that the strain energy stored due to axial force is given by UP is equal to integration of P square L upon 2 AE. Here AE is nothing but what? Axial rigidity. Strain energy stored due to shear force is given by US is equal to integration S square L upon A into 2 into A into G. Now here AG is shear rigidity. Then strain energy stored due to the bending moment is given by Um is equal to integration m square ds upon 2 EI. Now here EI is the elasticity. Then the strain energy stored due to the twisting moment is given by Ut is equal to integration t square ds upon 2 Gj, and here Gj is torsional rigidity. And total strain energy is given by the summation of all these four strain energies, that is U is equal to Up plus Us plus Um plus Ut. Now let us see Castigliano's first theorem. According to Castigliano's first theorem, the partial derivative of the total strain energy with respect to the applied load gives the displacement in the direction of load at that point. Now if you see here in this cantilever beam, there is a point load at this free end, and according to this theorem, the strain energy, as we know that the strain energy due to the moment is integration of m square ds upon 2 EI. Now here the partial derivative of the strain energy with respect to the applied load P, you will be getting the deflection. And by partial derivative of this strain energy with respect to the applied load, you will be getting m dm upon into dm upon dp. Now this 2 gets cancelled, and by simplifying, you will be getting delta is equal to integration of m dm upon dp dx upon ei. And this one is for the slope. Now this one is for the deflection. For the slope, if you are making integration m dm upon dp, you will be getting here dp is nothing but what? Your moment. If you are taking the partial derivative with respect to the moment, you will be getting the rotation or the slope. Okay, this was nothing but what? Castigliano's first theorem. Again, let us see the partial derivative of the total strain energy with respect to applied load gives the displacement in the direction of load at that point. Okay, this deflection, partial derivative of this strain energy with respect to applied load give you the deflection, and partial derivative integration, the partial derivative of this strain energy with respect to the moment will give you the slope. Castigliano's second theorem, let us see the partial derivative of the total strain energy with respect to the redundant reactive component is equal to 0, and this theorem is of minimum strain energy and it is used for the indeterminate structures. Most of the cases we are using this for the indeterminate structures. Now as we know that according to this theorem, if you are taking the strain energy and the partial derivative of the strain energy with respect to redundant, for this case this Rb is the redundant and we are taking this partial derivative of this strain energy with respect to Rb, this term must be equal to 0. That is integration m dm upon dou Rb dx upon ei, this term equate with 0. Now by using this, we are solving some simple problems, standard formulae to find out the deflection. As we know that the cantilever beam subjected to an point load at free end, the standard formula to find out the deflection is WL cube upon 3I. Now let us see by using the strain energy how to find out this formulae. Now here let us consider one section over here XX, and at a distance x from support B, and the moment which is caused due to this load, it makes an clockwise moment over here. As we know that about the section, if the moment is clockwise to right side, it treated as negative, and the section to the left side moment, it is also treated as negative. That's why this moment is minus W into X. The partial derivative of this moment with respect to the applied load W is minus X, and this X varies from 0 to L over here. Now put this value in above equation, you will be getting this delta is equal to partial derivative of this strain energy with respect to applied load integration m dm upon dw dx upon ei. Put the value, moment is of minus wx, and the partial derivative of this moment with respect to applied load is minus x. Multiplication of these two becomes a integration of w x square, and as we know that integration of x square is x cube upon 3, limit varies from 0 to L. Now by simplifying, what we will be getting, w L cube upon 3a, and that is nothing but the standard formula for the cantilever beam carries an point load at free end, and by using this strain energy method also you will be getting the same value. Now if the cantilever beam carries an UDL, now let us see, this cantilever beam carries an UDL W per meter run. Now for our simplification, we are applying this P load, zero load at the free end to find out the deflection at this end. Now as we know that the moment at section XX is given by, due to this UDL, W into x by 2, again due to point load, P into x. By simplifying this term, W x square by 2 minus P into x. Now the partial derivative of this moment with respect to applied load P. Now here only in this term the P is term, that's why the partial derivative will be minus x, and limit varies from this x varies from 0 to L over here. Now again simplify the terms. Now before simplification, as we know that, put the values moment and the partial derivative of this moment is minus w x square upon 2 minus px, and the partial derivative is minus x. Now here put the p is equal to 0, it means that this term will be vanished. Okay, only the remaining term is there. Multiplication, let us multiply this term, minus w x cube upon 2. Now here w upon 2 ei is the constant term, let us take it outside, and the integration of x cube, you will be getting x raised to 4 upon 4, limit varies from 0 to L. Now put the values and simplify the term, you will be getting what? Your delta is equal to w L raised to 4 upon 8 ei, and that is nothing but the standard formula for the beam carries an UDL, and you'll be getting the deflection at free end, and by using this method also you'll be getting the same value. Now if the cantilever beam carries an moment at free end, moment m at the free end, again we are applying this P load. Here this P load is 0 for our simplification. Now again let us consider this XX section over here, and moment about this section will be getting about P into x and the moment, and the partial derivative of this moment with respect to load is minus x, and partial derivative of this moment with respect to moment is minus 1, and limit varies from 0 to L, as we know that this section is varies from 0 to L. Now you'll be getting delta is equal to partial derivative of strain energy with respect to applied load, that is integration m dm upon dp. Put the values, moment is of minus m minus px, and partial derivative is of minus x. Now simplify the term, you'll be getting the deflection. Put the value of p is equal to 0. For our simplification, we are consider this load, and by simplifying, minus m multiply with minus x, you'll be getting mx, and integration of x is x cube upon x square upon 2, and put limit from 0 to L, you will be getting m L square upon 2ei. That is nothing but the standard formula for the cantilever beam carries an moment at free end. You will be getting this deflection, and by using this method you will be getting the same value. And for the slope, as we know that we are taking this partial derivative with respect to moment again, and the value is of minus 1, and integration of constant term is x, and that's why limit varies from 0 to L, and you will be getting ml upon ei. The same value as general standard formula is there. Now let us solve one simple problem by using this strain energy method. Now if you see here, this one is the prop cantilever beam carries an UDL of 10 kN per meter run, having the span of 3 meter, and it carries an spring having the stiffness kb is equal to E upon 2 kilonewton per meter. And as we know that deflection is nothing but what? Integration m dm upon dr dx, and this term must be equated with what? Ei delta b, and here this is nothing but what? Your deflection of spring, it must be equated. Now here for our simplification, as we know that the deflection of your spring is given by reaction divided by the stiffness, and stiffness is nothing but what? 2 E upon 2, and the value is, now put this value in above equation, Now in equating this two term, here ei gets cancelled, remaining term is only minus 2 rv. Now for your simplification, again let's take moment of the external load and reaction. Now if you see here, if we are taking this section over here, xx reaction rb, it makes an anti-clockwise moment. Due to this udl, it makes an clockwise moment, and you will be getting these values rb into x minus w x square by 2, and the partial derivative of this term with respect to the redundant rb is x only. Now the multiply this two term, moment into partial derivation. Now simplify this term, multiply this x to inside of the bracket, rb into x square minus 5 into x cube is equal to minus 2rb. Now here rb is constant, x cube, integration of x square is x cube upon 3, integration of x cube is x raised to 4 upon 4, limit varies from 0 to 3, 0 to 3. Now put the values and simplify the term, you will be getting the reaction rb. And to find out the reaction Ra, total load, that is 10 into 3 UDL, minus reaction Rb, that is 9.7, you will be getting the reaction Ra, that is 20.79. And to find out the moment at fixed end, as we know that the geometry is like this one is the UDL having this intensity of 10, span is of 3, and here the Rb is there, and we have to find out the moment at support A. Now Rb into 3 is the anti-clockwise moment, and due to this UDL 10 into 3 into it acts at half of the length, that is 1.5. By simplifying the terms, put the value of Rb over here, and you'll be getting minus 17.4 kilonewton meter moment at the support A. And we have to overlap the center span moment. As we know that it carries an UDL, the standard formula is of WL square upon 12. Now intensity of W is 10 and the span is of 3 divided by 12. If you simplify this one, you'll be getting the 11.25. Now by using these terms, we are able to draw the SFD and BMD. As we know that the standard reaction is 20.8 over here, 20.8. It goes down due to the UDL up to 9.2 over here, and due to this reaction it again becomes a 0 over here. This is nothing but our here shear diagram. And bending moment diagram, as what we have calculated, moment at A is 17.4 and joined by a straight line over here, and overlap the central span moment, that is 11.25, what we have calculated right now over here, 11.25. Now here uncommon portion is nothing but what your actual bending moment diagram. This hatch portion is showing the actual bending moment values of your beam. By such a way we can able to find out reaction, moment, shear force, all these values by using the strain energy method. Okay, thank you for the listening.